Swayam Prabha. Digital India. Educated India.
Welcome back to lecture 13, part 4. In this lecture, we will be continuing with the previous problem and also we will be solving a couple of problems depending upon the availability of the time. So, in the previous lecture, we have solved, we had calculated up to this point, that is the specific volume using the formula Vf2 plus x into Vfg2. Vfg2 is the difference between Vg2 and Vf2. Okay. So, this is 0.009127. So, we have stopped at this point. Next, we have to calculate the refrigerant viscosity of the refrigerant, that is after throttling. So, similarly here also, since after throttling it results in a two-phase flow, that is a combination of both liquid and vapor, we need to calculate the liquid viscosity as well as the vapor state viscosity. So, this is the liquid state viscosity. So, using the formula, we have to calculate this one. Mu Vf2 is 2. This is the equation which is taken from the table, because most of the tables may not have the viscosity values, especially the table which I am referring. It has only enthalpy, entropy, specific volume, and some will have specific volume values for both liquid and vapor, and it depends upon the publisher and the author. So, using the empirical relation, we have to find out the dynamic viscosity or the viscosity of the refrigerant liquid. Okay, so, this is liquid refrigerant, and this is the viscosity of the refrigerant in vapor. This is vapor refrigerant. So, this is both are viscosity. So, next, since the dryness fraction is given in the question as 0.21, I will be similar to specific volume, we can write, so similar to specific volume, that is viscosity after expansion, that is mu2, which is equal to mu f2 plus x2 into mu f g2. This can be written as mu f2 plus x2 into mu g2 minus mu f2, where mu f2 and mu g2, mu f2 are calculated in the previous slides. Mu f2, mu g2 are calculated in slide 8. So, we have not slide number 8, it is in slide number 4, slide number 3, it is in slide number 3, slide 8. Slide number 3. So, substitute the values. X2 is given, x2 is equal to 0.21, which is given in the problem. After calculating the refrigerant viscosity, both liquid and vapor, so we need to find out the viscosity of the mixture, that is which is in the two-phase region. So this is the liquid viscosity and this is the vapor viscosity. So mu F2 is the liquid viscosity. Let me go to this. So mu F2 is the liquid viscosity and mu G2 is the vapor viscosity. So when you substitute the values, so here you will get, so this is mu G2 minus mu F2. So you will get mu 2 is equal to 0.000274 Newton second per meter square. 0.000274 Newton second per meter square. So this is the viscosity of the refrigerant mixture, which is in two-phase region. Next, similarly, how we found the velocity before throttling, we have to find out the velocity, the refrigerant after throttling. So using the continuity equation, m dot equal to rho AV, rho is 1 by specific volume, same formula. So V2 is equal to velocity after throttling or expansion, after throttling or expansion process. So this is V2, m dot is equal to rho AV. So V equal to m dot by rho 2 into A. Rho 2 is nothing but 1 by rho 2 is nothing but small V2, that is specific volume. This is specific volume. So this can be written as m dot by A. 1 by rho 2 is small V2, so multiplied by small V2. So substitute the values, you will get the velocity after throttling. Okay, so again this will be m dot, not m, this is m dot. 43.9 meter per second. 43.9 meter per second. 43.9 meter per second. So once we find the velocity, we can find the Reynolds number after throttling. So that's what I am going to find. Reynolds number RE2, Reynolds number after throttling. So this is Reynolds number after throttling. RE2 is equal to rho 2 V2 D by mu 2. Rho 2 is 1 by small V2. So this is V2 D divided by mu 2 into small V2, specific volume. So all the values, velocity we have found, diameter is given, mu 2 we have found, and small V2 also we have found. So we can find out the Reynolds number. So it will come to 28,614. 28,614. Once we know the Reynolds number, we can find out the friction factor. Friction factor. So this is also after throttling. After. So that is F2. Before throttling is F1. So 0.33 divided by Reynolds number after throttling to the power of. The formula is same. Only I will be substituting the Reynolds number after throttling, that value. So we will find out the friction factor as, this is the friction factor, F2, 0.0254. 0.0254. 0.0254. So next we will be finding the average of the velocity and the average friction factor. It's a quite lengthier problem, but it's a practical problem which I have taken. So the average friction factor, that is the summation of F1 and F2 by 2, and average velocity we have to find. This is, so this is the average friction factor is F. and average velocity is V. If you want, we can take F suffix AVG and we can write V suffix AVG. Whichever is convenient, the learners can use that one. So I have taken F as the average friction factor and V as the average velocity. So it's a simple calculation. So the average friction factor is 0.0241 and the average velocity is 24.1 meter per second. Next, we have to calculate the pressure drop. There are two types of pressure drop. One is due to the acceleration, another one is due to friction. So the pressure drop due to acceleration is calculated using this formula. Delta P suffix A refers to pressure drop due to acceleration, that is m dot by A into V2 minus V1. So let me write it here. Pressure drop due to acceleration, that is delta P suffix A, which is equal to m dot by A into V2 minus V1. All the values are known. All the values are known. Just you have to substitute. M dot is given in the problem. A is pi by 4 d square. V2 we have found out. That is the velocity after throttling. V1 is the velocity before throttling. So all these values are known. So when you substitute, you will get 1.9 bar. All these values are known. So delta PA is equal to 1.9 bar or 1.9 into 10 power 5 Newton per meter square. Next one is pressure drop due to friction. Pressure drop due to friction is the total pressure drop minus the acceleration, pressure drop due to acceleration. Pressure drop due to friction. So this is delta P of F. This is equal to total pressure drop minus pressure drop due to acceleration. The total pressure drop is nothing but the difference between condenser pressure and evaporator pressure and this delta PA time. All these values are known. We have taken the condenser pressure and the evaporator pressure from the R22 table in the previous lecture. So PC and P values were taken from R22 table corresponding to TC is equal to 40 degrees centigrade and TE is equal to 5 degrees centigrade respectively. So refer previous lecture, that is lecture 13 part 3, lecture 13 part 3. So here I will be directly substituting the values. Therefore the frictional pressure drop is equal to condenser pressure is, I think it is around 15.8, 15 point. Anyway, for your reference, learners, I have taken, this is the values. P 15.3 bar and evaporator pressure is 5.8 bar. 15.3 bar minus 5.8 bar minus pressure drop due to acceleration. Pressure drop due to acceleration is 1.9 bar. Please ensure that all the values are in same unit. So this is condenser pressure, this is evaporator pressure from the previous table, or you can refer slide number. This is slide number 7 and 8. Slide number 7 and 8. Slide 7 and 8. So this is the pressure drop due to friction. So the pressure drop due to friction comes to 7.6 bar. 7.6 bar. So this is nothing but when you 15.3 minus 5.8 minus 1.9 is 7.3 bar. 7.3 bar. Sorry, 7.6 bar. 7.6 bar. This is 7.6. Now we can calculate the incremental length. The formula, this is the formula. Delta L is equal to delta PF into 2D incremental length is equal to, that is delta L equal delta L pressure drop due to friction into 2 times diameter divided by m dot, this is m dot by A into F into V. M dot by A into F into V. Here F is average friction factor and V is average velocity. So all the values are known. This is known. This is given. This we have calculated. This is given. This we can pi by 4 d square. And this is calculated. So substituting the values, you will get the incremental length of the capillary tube as 0.887 meter. 0.887 meter. 0.887. So quite lengthier problem. It's a practical question which I taken from the real-time application. So this is the parameter which we have to find. So let us move to the next problem. Select a suitable thermostatic expansion valve based on the following data. So the type of refrigerant given is R134A. Cooling capacity is given, that is the evaporator load, that is 6 kilowatt. Evaporator temperature is minus 10 degrees centigrade. Subcooled liquid refrigerant temperature is 20. Pressure drop in liquid line evaporator, that is delta P, 1.5 bar. So first step is to determine the pressure drop across the wall. So this is also a practical application oriented question. So step 1, pressure drop across the wall. That is, the refrigerant is given as R134A. Let us write the given data. Given data, refrigerant is R134A. Evaporator temperature is minus 10. Let evaporator temperature minus 10. Condenser temperature is 30. Condenser temperature is 30 degrees centigrade. Cooling capacity is given as 6 kilowatt. 6 kilowatt. So the pressure drop across the wall, that is the total. That is the condenser pressure minus evaporator pressure minus delta P. I think that is also given. Delta P is given. This is given in the problem, 1.5 bar. So this is also given, 1.5 bar. So minus delta P. Now this condenser pressure and evaporator pressure have to be found out from the R134A table. From R134A table. From R134A tables. At condenser temperature is equal to 30 degrees centigrade. The condenser pressure have to be read out. And similarly, at evaporator temperature is equal to minus 10 degrees centigrade. The evaporator pressure have to be. This is the R134A table. Corresponding to 30, the pressure is 7.7 bar. Okay, I think I have taken the values corresponding to 30, see here, 7.7 bar, and corresponding to evaporative temperature, it is 2 bar. Let us mark these values in the table. Corresponding to 30, this is 30, 7.7 bar. Okay, let me underline it. 7.7 bar. And corresponding to minus 10, this is minus 10, it is 2 bar. That's what I have written there. So substitute the values, we will get 4.2 bar. So therefore, substitute the values. So this you will get it as delta P total is equal to condenser pressure is 7.7 bar minus evaporator pressure is 2 bar minus delta P is 1.5 bar. So we will get the total pressure drop across the valve as 4.2 bar. So this is step 1. The second step is determine the required valve capacity. Determine the required valve capacity. So this is the step 2. Determine the required valve. Condenser temperature we know 30. The subcooling temperature is also given. This is given in the question. So temperature of subcooling is 20. Temperature of subcooling is given as 20 degrees centigrade. So next we have to, step 2 is valve capacity. Valve capacity, that is Q valve. So for that, the degree of subcooling is determined. Delta T is, that is Tc minus Tb, that is 10 degrees centigrade. This is delta T. And from the table 5b, manufacturer catalog Castle. So this is the manufacturer of the, so I have taken the table 5b. So this is table 5b. This is the manufacturer. So now here you can see this is delta T of subcooling, delta T of subcooling. So the calculated delta T of subcooling is 10 degrees centigrade, 10 degree centigrade. So this is 10 degrees centigrade. Corresponding to 10 degrees centigrade, the correction factor is 1.08. This is from the table. This is the value. Next, using this one, I will find out the valve capacity using this evaporator cooling load divided by the correction factor. So Q valve is equal to evaporator heat load divided by, I think, F sub. This is F sub. This is the term. Okay. Correction factor due to F sub. So this has to be taken from table provided by the manufacturer. So when we calculate this one, it comes to 5.5 kilowatt. 5.5 kilowatt. Then the third step is the estimating the orifice size, determining the required orifice size. Determine the required orifice size. So I will be using another table that is from the manufacturer catalog, Castle. So for table 5A. So we know the evaporator temperature minus 10, which is given. Delta P total we have calculated. And the valve capacity we have just calculated, that is QE by the correction factor. So based on this one, let us go to this one. This is table 5A. This is pressure drop across the valve. For example, this is pressure drop for evaporator temperature 10. Across the valve corresponding to evaporator temperature. This is our given temperature. So here, these are all the pressure drop. The pressure drop the total pressure drop is 4.2 bar and wall capacity 5.55 kilowatt orifice code. So it is 2205. There is one, I think it is 2205. The pressure drop is, the calculated pressure drop is 4.2 bar. So it comes around here, pressure drop across the wall. This is the orifice code, this is the evaporator temperature. So this is the orifice code. So accordingly, we have to select this one. Q valve is 5.55 kilowatt. 5 point. This is the series. This is the series which is selected. 2205. 2205. If you see the previous table, this table has, this is the evaporator temperature for plus 10. This is the evaporator temperature for 0. This is the evaporator temperature for minus 20. This is for minus 10. So according to the given data, you have to select it, and we have to select the, and similarly the pressure drop. Here the pressure drop is, our pressure drop is around 4 bar. So we have to check this one. Corresponding to this one, the pressure drop is around 4.2 bar. Q valve is 5.55 kilowatt. So here it comes around 5.8. So corresponding to the pressure drop 4.2 bar, evaporator temperature minus 10 and 5 point. We don't have the exactly 5.5 wall capacity in the table. So I have taken the next highest 5.8. The orifice code series is 2205. So with this, so let me write this one. Orifice, use table, use table 5A manufacturer, provided by the manufacturer. Of course, the table number will differ according to the vendor or the supplier. So accordingly, it is determined. So let me complete the part 4 of the lecture number 13 with this. Thank you.